Please welcome Sarah Jones, Zero Carbon Capital.
Hello everyone, so I'm Sarah from Zero Carbon Capital, and we invest in the earliest stages in visionary startup founders who have scientific breakthroughs for decarbonization. And it's my pleasure to nominate and introduce Shayna from Level 9. So we met Shayna and Emily a year ago and saw that they were solving a huge problem: how to enable the low carbon sustainable alternatives to petrochemicals. Their breakthrough nanozyme technology converts complex biological feedstocks into biochemicals as a low emissions alternative to fossil-based chemicals. So in the urgent mission we have to stop climate change, this is one of the key steps that we need to take to decarbonize the petrochemicals industry. And Shayna and Emily, the founders of Level 9, we've been working with them now for a year, and they're exceptional founders, and they're really driven to improve the chemicals industry. And they are pioneers in nanozyme development, this breakthrough scientific innovation that they're developing. And they are excellent visionary founders who we're supporting, and it's my pleasure now to introduce Shayna from Level 9.
Breaking the wall to fossil-free chemicals. Shayna Quigley, Level 9.
The chemicals industry has a catalyst problem. Almost 90% of all chemical processes require a catalyst to function, but companies face a difficult trade-off between traditional catalysts on the one hand and enzymes on the other. Traditional catalysts, which were developed for the oil and gas industry, are very cheap, but they also tend to be very crude, and they require immense amounts of heat and pressure to function. Enzymes, or biocatalysts, on the other hand, which you'll also find in your body, are far more targeted and specific in the kind of reactions they can do, but they tend to be expensive and extremely fragile to the reaction conditions. This is a huge bottleneck in the industry, holding back innovation and holding back companies from achieving their climate targets. At Level 9, we're bridging this gap. We're leveraging bio-nanotechnology and quantum chemistry to develop the world's first nanozymes, next-generation catalysts that combine the specific and targeted reactions of an enzyme with the stability of traditional catalysts. So how does this work? We're building on the insight that less than 1% of an enzyme's surface area or volume is actually responsible for the catalytic reaction. This is called the active site. Our nanozymes are, in essence, advanced nanomaterials that mimic just the function of just this active site, but synthesized in such a way that they have built-in stability to the kinds of harsh reaction conditions that would normally kill off an enzyme. This way, our nanozymes combine the best of both worlds, opening up entirely new possibilities in terms of sustainable chemical production. Our first use case is in biorefinery, which is the production of chemical building blocks from biomass as opposed to fossil fuels. Scientists have been trying to use enzymes for this use case for decades because it's such a huge opportunity, but so far with limited to no success, and many scientists have given up hope that they ever will. In contrast, in just a couple of months, we've developed a process based on our first nanozyme that already outperforms the current state-of-the-art lignin depolymerization process in terms of yields, economics, and sustainability. In terms of traction, we're currently working with some of the leading biorefineries across Europe to scale up and commercialize this first process. We expect early next year to already have a pilot-scale demonstration done. Early next year. However, we believe that the potential impact of our technology goes far beyond that. We are envisioning a next-generation catalyst platform powered by quantum chemistry and machine learning, where we can rapidly develop novel nanozymes to address problems across a wide range of use cases and industries. We've already shown with our first nanozyme that we can solve the stability problem of enzymes in biorefinery, and we can now start to imagine what other things we can start to solve. Imagine, for instance, a nanozyme that can combine the power of 2, 3, or even more enzymes into one supercatalyst. Or an enzyme that doesn't require cofactors that make most enzymes prohibitively expensive for industrial use cases. Or maybe even one day we can develop a nanozyme that can catalyze a reaction for which no enzyme exists in nature. We are reimagining enzymes from first principles, and the potential possibilities are endless. So who are we? My name is Seadna Quigley. I'm the co-founder and CEO of Level 9. And before starting the company, I have helped build and scale 2 or 3 companies, in the circular bioeconomy space. My co-founder and CTO, Emily, she has a PhD in bio-nanotechnology from one of the field's leading research institutes, and an interdisciplinary background that spans biochemistry, protein design, protein crystallography, and biomimetics. Since founding the company a year and a half ago, we've raised more than 2 million euros, and we've built a team of highly talented interdisciplinary scientists who have the skills and the backgrounds to build this vision. We're Level 9. We're developing next-generation catalysts to enable the green molecules of tomorrow. Thank you very, very much.
Cool. Nice. Next level. Fantastic. Okay, then next questions. Let's go. Who wants? Okay, Iris will start.
Thanks, super interesting. You kind of pointed it out at the beginning already, but like refineries, also biomass refineries are typically not necessarily designed to work with enzymes or biocatalysts. So I was wondering if there's any sort of retrofitting you can do to put your enzymes in traditional reactors, or whether you need to change existing infrastructure to facilitate them.
And by traditional reactors, you mean more like fermentation-based?
No, like not necessarily bioreactors anyways, because you talked about biomass refining, right? So I mean more like traditional oil and gas type refineries.
So we're not focused on, we haven't looked into oil and gas type refineries, and it's also like that's different kinds of temperatures, different kinds of pressures. We focus very much on biorefinery at the beginning. However, what we do know is that our nanozymes, they're very flexible and modular, and they're easily immobilized into different systems or recoverable as well. So they are very flexible in terms of what kind of systems we can put them in. That is definitely true.
Thank you. Stefan, please.
In your presentation, you mentioned that there is a depolymerization of 60% roundabout. Yeah, that's at par with industry. Are you happy about it, or is your new technology also prone to increase that level to higher degrees, as you can find in other depolymerization processes?
So this is the benchmark that we've been using for now, and this is what we've managed to achieve this year. This is actually with a relatively minimalist nanozyme structure. We've also tried more advanced ones, however, and the performance is better. However, the cost then becomes an issue. So while we try to improve the process and try to bring down the cost of the second catalyst, we are actually quite confident that this is something that we can start commercializing, and that's what we're going to start doing in parallel. But yes, we do think there's a lot of room for improvement still.
Okay, next question. If I don't see the jury, I will open to the audience here in the fifth row.
Thank you. Just a quick question about the science. Is it like inorganic based or organic or a mixed? Because you talk about nano, but you don't say what.
It's mixed. So we look at the active site of an enzyme, and specifically we're targeting in the beginning metalloenzymes, which contain both. We've kind of moved away from the exact mimic, but we use both synthesized in a kind of a one-pot synthesis. So it combines both, yeah.
Okay. Another question? Okay. Well then,
thank you so much.
Yeah. Thank you very much.